That is get the recording going. Okay, so welcome. Thank you for allowing me to start a little late with you guys. I appreciate it. We're going to go into carburetors today and talk about these guys and the different systems and circuits and stuff in there. But before we do, I figured I'd just share something about the meeting I was just with. Regional Transit. You folks, living in the Sacramento area know, you've seen the buses around town, you probably know about RT or Regional Transit. I just wanted to let you guys know that there's a lot of opportunities for you guys. It says now hiring, we're looking for many positions. Regional Transit is looking to hire technicians. So what I wanted to share with you is that if you are taking the small engine class and you've started working on a small engine at home or anything like that, and you're like, hey, I kind of like this. This is pretty cool. I don't mind working with my hands. I don't mind maybe getting my fingers a little dirty, or I like diagnosing things, figuring things out. There's more opportunity in the automotive. And when I say automotive, I mean pretty broad terms, whether it's small engines or heavy duty or working on buses. There's more opportunity in this industry than I've ever seen in my career. So Regional Transit is looking for people, and they just said, hey, we're looking to bring in people, hire them, get them, working as an entry-level person where they're filling up the buses. Now, but most of their bus fleet, it runs on compressed natural gas. So filling up the buses, cleaning them, and then we're going to pay them to go to school and take a series of automotive and technical classes, and then move them from apprenticeship level to journeyman level. And so that's pretty neat to be able to go to school and get paid to go to school, get a certificate from the college, and move up to $30 an hour in about a year's time frame is what they're looking at. So pretty neat meeting. Now, I've had similar meetings with AAA, who's opening up service centers, throughout California, Northern California, and several other car industry organizations. So if you guys are taking this small engines class and you find that you like working with mechanical things, there's lots of opportunities on a variety of things that are open for technical people. Okay, so today's topic, of course, is all about fuel systems. And so if we go through the modules here, guys, we've gone through modules 1 and 2, and now we're really jumping in deep into modules 3. Now, last week we talked about air fuel ratios, and we'll get into that again today. What I'm going to do is I'm going to pick this up just right off of, I'm going to try to pick this off right off of our Zoom info. I'm going to go ahead, or not Zoom info, our Canvas page. Too many different online platforms, huh? So we can check that out, and I'll open up that screen share and make that a little bit better for you to look at here if I can. There we go, and new share, there it is. So we'll hit a few of these slides. We'll hit a few of these slides here from our engines presentation here, or from our fuel systems presentation. So the first slide is this, and let me just zoom out on that just a tad, and it's talking about hydrocarbons. And the long and short of it is that fuel is made out of hydrocarbons. Now, actually, the gasoline that you get from the pump, almost think of it as a recipe of a variety of things. It's not just hydrocarbons. There's fuel system cleaners and detergents. And we also know that we have some alcohol in our fuels. We were talking about that a little bit last week. But at the base, the majority of it should be hydrocarbons. And you can see that we have 8 carbons atoms here with a whole bunch of hydrogens. That's kind of your common HC molecule that would be in fuel. And so if you ever, let's say you get your car smogged and you look at your emissions printout and it talks about HCs. What are HCs? HCs are unburned fuel. Last week, we talked about 2-cycle engines and how they have a tendency not to run really clean. They just push raw fuel out the exhaust because of the way the ports and stuff work. They're bad on HCs, and that some of the fuel that goes in the engine just gets pushed right out the exhaust. So if you don't burn fuel, it's HCs. If you took a smog machine and you poured some gas on the ground and you sniff the smog machine over it, right? You let the probe over that, it would show a whole bunch of HCs on the exhaust. So whenever you can smell exhaust and it makes your eyes water, and you're smelling the HCs. Okay, so fuel is a mixture of a bunch of things, but it's largely a hydrocarbon base. All right, we'll clear out those drawings. So the other thing we like to say is that if everything ran perfectly, if our small engine ran perfectly, it would make carbon dioxide and water. I'm going to try one additional thing because I'm not totally happy with how our screen looks here. And I'm going to see if I can get it to look a little bit better. View. Rotate, let's see, full screen mode. Okay. I like that one better. Okay. So there we were. And now we don't have that banner across the top, and I just feel better about that. Combustion is a process where we're turning, basically we're taking air with some heat added to it and fuel, and we're burning that to get mechanical energy and move us down the road or mow our lawn or whatever, right? If that process happened perfectly, what we would get out of it as far as exhaust gases are concerned is we would actually get carbon dioxide, we would get some water, we would get some nitrogen, and of course, what's all the heat? Well, the heat is the energy pushing the piston down. So I think that's an interesting thing. If your engine ran perfectly, it would basically, as far as like exhaust emissions, what would it make? Basically carbon dioxide and water. However, our engines don't burn efficiently. They don't burn everything. So what do we really get? I'm going to put over here in a little text box, we're going to get some unburned fuel. So we have some hydrocarbons coming out the tailpipe. We're also going to have some hydrocarbons that if you look at the numbers and letters here, like hydrocarbons and then CO2, we're basically splitting up that hydrocarbon and taking that carbon atom and adding a couple oxygen to it. Well, let's say we don't fully burn it, we don't get CO2, we get CO, or carbon monoxide. And then we also end up with some oxides of nitrogen, some nitrogen basically sticking to the oxygen. So With that, we get these unwanted exhaust emissions. And these are the ones that if you get your car smogged, that they're on your smog test. And as we saw last week, that they actually emissions test small engines now at the factory as well. So those things are bad. But hey, even if your engine runs perfectly, it still makes carbon dioxide, and carbon dioxide is also considered to be a greenhouse gas. So it's an unwanted gas as well. And that's why in the automotive segment, there's been a big push to have vehicles be electric or hybrid, or go from a big engine to a smaller engine. And the reason you do that is that, hey, a bigger engine is a bigger pump. If I can make my engine smaller, it will be producing less carbon dioxide. So even if I put a catalytic converter on there and everything ran perfectly, and it was just making CO2 and water vapor out the tailpipe, I still want to minimize that CO2. Anyway, so a little bit of emissions theory. I wanted to wrap that in there, and it kind of gives you an insight of, if you're getting your car smog, some of the pass fail things that you would see on that emissions printout as you get your vehicle tested. All right. So fuel is made out of hydrocarbons, and that combustion process that happens is pretty darn dynamic. Now, last week we talked about air fuel ratios, right? And those air fuel ratios are pretty darn important. Looking for a little thing from my desk here so I can go over some air fuel ratios for you. So those air fuel ratios are pretty important. Our ideal ratio for gasoline happens to be 14.7 to 1. So what does that mean? Well, for every 14.7, or just about 15 pounds of air the engine brings in, so I'm going to put air. Guess I should have made it a different color than black, right? For every 14.7 pounds of air that you bring in the engine, what we would want to do is mix with it 1 pound of fuel. So I'll just write gas here. And that ends up being a good ratio where a gasoline powered engine is going to run good and make good power. It's also going to run efficiently. So see, it says most efficient right here, have about as complete combustion as it can have. So that also means not only does it run efficiently, but it runs as clean as it can. What you guys can see also here is, if I clear out those drawings, is that if I run different fuels, my ideal air fuel ratio, my stoichiometric or lambda 1 ratio, varies by what fuel I'm running. So let's relate this to the alcohol that we find in our fuel. See the air fuel ratio that's desired when I'm running alcohol? So what happens is I need a lot more fuel, or by comparison, less air in my mixture when I'm running alcohol-based fuels. Why? Because alcohol actually has oxygen worked into the molecular structure of the fuel, into the hydrocarbons. It's got some O2s in there. And so you need to run basically more fuel to kind of compensate for that. So having alcohol in our fuel essentially leans out the mixture, which can help make the engine run cleaner, but it can also affect our air fuel ratio and get us to where, if our small engine, its carburetor is tuned for this, now we're running too lean for that. And unless we have a computer that can compensate for that, that has closed, has, engine management that goes into closed loop where it can adjust its air fuel ratio, that throws us off. Okay, but this slide points out that, hey, we run different air fuel ratios for different fuels that we're running in our engine. You might drive around town and know some vehicles have a badge on them that says flex fuel. That usually means it can run gasoline or E85. Its fuel system has the ability to compensate for either one of those fuels. It also has fuel injectors that can handle the more corrosive nature of running those alcohols. So just a few things about gasoline. Remember, it's a mixture. There's all kinds of stuff in there besides hydrocarbons, from anti-icers and detergents and stuff in there. And there's also summer gas and winter gas. So one thing you guys might notice, if I can get my slides to back up here. There we go. If I get it to back up, is that you might have put winter gas in your engine during the wintertime. It ran good. If that gas can sat around for several months and now it's getting hot out, just the nature of the changing chemistry of the gas can make the engine run poorly. It's likely to ping and knock and have detonation problems running winter gas in the summer. And if you had summer gas and you go to fire up an engine in the cold days of winter, you're likely to have an engine that's hard to start because the volatility is different of the fuel. So if you're diagnosing an engine, one of your tech tips of the day is to always make sure you got fresh gas and pay attention that your gas is seasonal. And so just by having, some summer gas in winter conditions or cold weather conditions, that could be enough to make an engine be hard to start. If you have, gas that you got in the middle of August or even September, and now it's November, December, and it's cold outside, you're having a really hard time starting that engine, try some fresh gas. Never go wrong with having some fresh gas in your engine. Now, of course, one of the byproducts of burning fuel or hydrocarbons is carbon, right? That black soot that gets on top of the pistons in the combustion chamber area, that impedes, right? Hurts the engine's ability to cool, and over time can create issues. And that's why in today's fuel, we try to have some detergents in there to try to keep those carbon and fuel system deposits to a minimum. But that is still going to happen. And it's one of those things that, especially on a two-stroke engine where you're burning oil with the fuel, it's just kind of part of it. And that's, part of the reason the engine might need to be taken apart and serviced. And, is a clean, when you got it apart, you clean out all those deposits out of there. Okay. So this is a pretty neat chart, but I don't need to boggle your mind with it. It basically just shows you that, hey, when I run a stoichiometric ratio, that's also when the engine runs as clean as it can. So it doesn't matter what fuel you're running. When you're running stoichiometric, it's going to give you your ideal efficiency of the engine, and it's going to enable that engine to run as clean as that type of engine can run on that fuel. So moving right along, we talked about catalytic converters last week. Here's a great little shot of what the catalyst element in a small engine would look like. And hey, guess what? It looks the same in a car. It's a little monolith structure. And as the exhaust gases flow through it, that little brick that looks like a little brick with a bunch of holes in it, it's porous. The exhaust gases flow through it, and they continue to burn. They oxidize and they reduce, and it lowers the emissions. What's on that little catalyst element? Platinum. And this is why the cat thieves around town, unfortunately, go around and steal people's catalytic converters off their cars, because that little brick is worth some money because it's made with precious metals. Again, that's why the small engine manufacturers don't want to put those on their engines if they can avoid it, because it adds to the cost of the engine. But that little brick right there does lower exhaust emissions quite considerably by lowering HCs and CO and oxides of nitrogen. It really works amazingly well. But I will also say that if you have a problem with your engine, it can burn that up. That little brick is trying to burn up any smog, any emissions the engine doesn't burn. So if the engine is running poorly, you can actually melt this thing down. You can also, let's say your engine's smoking, you could clog that catalyst up. And I've had some engines, both in small engines and in cars, that had a lack of power because they had restricted exhaust from the catalytic converter getting clogged up. So that's something to think about as well. Notice it says catalytic element retainer screen. A lot of engines, even like your 2-cycle engines, it doesn't have a catalytic converter, but it might have a screen in the exhaust, a spark arrestor in the exhaust. That little piece of wire screen keeps sparks from flying out the exhaust and causing forest fires and, you know, fires in your yard, that type of thing. Especially on the 2-strokes, make sure that little screen. So tech tip of the day number 2 is if there's any type of screen in the exhaust, make sure it's clear. Especially on the 2-strokes, that little spark arrestor screen will clog up and that will restrict your engine's power output. All right, we'll clear those out of there and we will keep our presentation going. So this is that summer gas versus winter gas deal. Remember, summer gas would make it hard to start in the winter. Winter gas in the summer would make the engine run poorly. Another problem with small engines, it leads to vapor lock. They talk about it in the Briggs and Stratton videos where you end up with little bubbles in the fuel, and that gets increased with the temperature outside and all the vibration. And that can basically make an engine act like it's running out of fuel. In fact, back in the day, this was even a problem on our cars, and the old school mechanics trick was to put a bunch of clothespins. That's what I'm trying to draw here. It doesn't look like a clothespin, but you get the idea. They put clothespins on the fuel line, or they might wrap the fuel line with aluminum foil to try to act as a heat sink and to shield the heat from the fuel line to reduce the vapor possibility of vapor lock. So that's an issue. If you have an engine that when it gets really, really hot outside and the thing acts like it's running out of fuel and it keeps shutting off, you could be fighting a vapor lock issue. And of course, if you had the wrong blend of gasoline in there, that would just only add to that issue. All right. Now, this slide is talking about atmospheric pressure, and it's not a conspiracy or anything. Yes, I know if we look at this number right here, we see 14.7 again. It just happens to be a coincidence that the stoichiometric ratio for gasoline engines is 14.7 to 1. Atmospheric pressure at sea level is 14.7 psi. So what I want you to think about is, how do we get that pressure? Think of all the atmosphere that's stacked up on you and me and our small engines and our carburetors for that matter, when we are running there at sea level. Of course, as you go up in elevation, you lose atmospheric pressure. So that's one of the reasons why you lose power from your engine as you go up in elevation. The other thing to think about is that on the intake stroke of the engine, now I know I've hit you up with 2-3 weeks of intake, compression, power, exhaust. When the engine goes on intake stroke, what pushes the air-fuel mixture into the engine? This atmospheric pressure does. Okay, so it's not that the engine is sucking in the air-fuel mixture, is that the pressure created in the engine is less than atmospheric pressure outside, and it's the high pressure outside that causes that air-fuel mixture to move in there. All right. Well, we take advantage of this air pressure deal all over the place in our carburetors as well. So here we're just talking about how fluid flows from a high pressure area to a low pressure area. That's just physics, right? That's how stuff works. Here we have a carburetor, almost just like the one I'm holding in my hand right here. And what I want you guys to realize is that the way the carburetor works is it's all about changes in pressure drawing fuel into the incoming airstream. So if I advance this slide again to the next slide, and we look at it, this slide talking about Bernoulli's principle, really what it is it's like an airplane's wing. In that, if I look at my carburetor, on the inside area of it, in the center of it, there's this part where it gets real skinny. That skinny part of the carburetor is called the venturi. And that venturi essentially is like the wing of our airplane here. Now, the wing of our airplane creates lift. How does it do that? Well, as air is flowing over this wing, it has a longer distance to travel on the top of the wing than it does on the bottom of the wing. But guess what? However much air is going through the wing, over the wing here, I have to have the same amount of air on the other side. So that the air that takes the longer path, it actually has to speed up as it goes on the top side of that wing. And as it speeds up, it creates a low pressure area. And that low pressure is what creates lift. So what we've done here is it's like we have two airplane wings on top of each other, causing the air to speed up in the middle. That's not going to create lift, but what it is going to do is it's going to cause a low pressure area in the center of the carburetor. That low pressure area then is going to be enough to draw fuel from this bowl on the bottom up to the center of the carburetor, to basically draw fuel up through the carburetor. And that's how the main system of the carburetor works, is off of that venturi. If I can find my screwdriver here that I had one and I dropped it in the shop, and I should have another one right here. I have a modified one. So we will use this one. And we'll look at this little carburetor that I have right here. And this was off of a mini bike engine. And the student I had decided that he was gonna replace this carburetor. And why I grabbed it is it really matches well with, if I clear these drawings, really matches well with this picture right here, where it's got a float bowl on the bottom. So let me see if I can get this thing to work. I'm going to switch over to my other camera if I can here, get my zoom controls going. Let's see here. Video. Boom. All right. Camera number 2. And now what we're going to do is we're going to change this camera's angle so that it can look down not at my coffee cup or all my cables and different things on my desk, but at this carburetor here. All right. And what we will do is we will pause the share and change that out. Oops. If we make this big. Okay, so now let's see if I can get that going. All right, so now we're looking at this carburetor here, and it looks just like that cutaway we had in the video. And what you can see on this thing is, gosh, it looks pretty dirty. Now here's where the air first flows in, and what I notice here, and it maybe is not coming across on the video, but it's dirty on the inlet side of the carburetor. That's not a good sign, because that means my engine likely has been sucking in dirt, and that's going to cause wear and tear on my valves and piston rings and cylinder walls. Here I can see some fuel staining. As fuel goes bad, it turns into a varnish. And so I can see that there. And so like this thing's been through the gamut here, so to speak. And what we're going to do is we're going to take this carburetor apart here. And I have my custom made 90-degree screwdriver here. I'm taking off the float bowl. And one thing I like about small engine carburetors is, there's not 100 screws to them. I mean, they're pretty simple. And if you guys are just getting, accustomed to working on mechanical things, maybe before you take your whole engine apart, just focus on doing that carburetor activity. It'll be a little bit more palatable, if you will. It'll be a little bit easier to start off with. Okay, so I've taken off the screws to the float bowl. The float bowl is like a temporary little storage tank for the fuel before it enters our engine. And I guess I should point out one thing that I think is important. Tech tip number 3, if you will. And if I can maybe move that up a little bit. Tech tip number 3, see how it's got this little fitting down here? It would have a gas line that would go down. And this screw here is a float bowl drain. So if I didn't want the gas to sit in my carburetor and go bad during the winter or whenever I wasn't going to use my engine, what I could do is open up this drain my gas tank, but I could also drain out all the fuel out of my carburetor and it would flow out of that little fitting right there on this particular carburetor. This is something that most people don't do. Heck, even sometimes I forget to do it. And it causes a lot of headaches because the carburetor gets all gummed up on the inside. Like we can see, this one is all nasty and gummed up because fuel was left to go bad inside the carburetor. It crystallized, it first varnished and crystallized in there. So you can see the float bowl's all gummed up. Here we can see the float mechanism of the carburetor. I'm going to pop my float pin out, hopefully. There it goes. Here's my actual float valve. That guy's out of there. Needle and seat, but you can see all that varnish and discoloration. So if I went to run my engine with this, it probably wouldn't run at all, or it might start and die, but it's pretty clogged. This carburetor needs to be cleaned. I've told you guys multiple times that a good 70–80% of your small engine problems are related to fuel system issues, and the bulk of those are related to dirty or defective carburetors. The passages inside these carburetors are pretty small. Now, this is for a mini bike, so it's bigger on the inside than your average small engine carburetor because it's going to consume more fuel. But still, these are pretty darn small passages on the inside of this carburetor. That and you can see that, hey, you didn't drain the fuel out of this thing, you didn't run any fuel stabilizer, it was just allowed to evaporate away, and it turned to varnish and crystallization and really clogged up this thing and did a number on it. Here's my main metering jet. Here's my pilot jet or low speed jet, idle jet, if you will. I'll go ahead and see if I can loosen those jets up and spin them out of here. And all this stuff, I would take it apart and I drop it preferably in an ultrasonic cleaner. But at the very least, I would take a can of like brake system cleaner and spray it through all these passages, and maybe get a little old toothbrush, not the toothbrush that you're currently using, but maybe your old one, and kind of scrub this out really good. If I look down the body of the carburetor, you can see that it does get smaller in the middle. In fact, it's probably more evident as we were talking about the Venturi. If I look at the carburetor this way, you can definitely see it gets smaller in the middle. And this little piece that maybe is hard to see right here in the bottom, that's where the fuel gets discharged out of that thing. All right, let's move this back to the slides, and I'll jump back and forth between this carburetor and our carburation slides. So to do that, we will change the video back to this one. Boom, there we are. And we will get our screen share going again. Let's make sure that that's working. Okay, that looks pretty good. All right. So we talked about how the Venturi system worked, and we've looked at a carburetor. Now you've seen the float bowl, you've seen a Venturi, you've seen some of these components on a real carburetor. And it's all about speeding up the air through the carburetor, creating a low pressure in the carburetor that will be low enough to draw fuel through the carburetor and mix the right amount of fuel with the right amount of air entering the engine. So the other thing to think about is the only thing a carburetor really knows is airflow. For a certain amount of airflow, a certain amount of pressure drop is going to be created, and it will draw in fuel with that. So the carburetor doesn't know how dense the air is. It doesn't know what the elevation is. It doesn't know, what you're doing with the engine or what the displacement is. It doesn't even know if it's a 2-stroke cycle engine or a 4-stroke cycle engine. It knows if I have X amount of air flowing through it, that air will speed up by a certain amount, and then that will create a certain pressure drop and mix fuel with the air. And this is why the trend has been to go to electronic fuel injection, because then we have a network of sensors that can monitor things like the outside air temperature and the density and the temperature of the engine, and fine tune the amount of fuel we're giving the engine based on what conditions that engine happens to be operating in. All right, but the vast majority of our small engines, they're just going to be using carburetors. So here's a carburetor design here. This would be an older one where we have a screw that basically we can screw in or screw out to regulate how much fuel flows through the main metering system and into the engine. And so it allows us to adjust the air fuel mixture, in that if I unscrew the screw, right? If I turn the screw, let me get my drawing tools going again. If I turn the screw counterclockwise, that would unscrew the screw, it would move it out. And what would happen is I would get a lot more fuel than could go through this passageway and be delivered in the incoming airstream. And older engines commonly had this design. What was great about this is if you took an engine and now you're going to operate it up in Tahoe, you could, with a turn of a screw, lean out that mixture and adjust for the conditions that engine was operating in. So it was very adjustable and easy to use. But if you didn't know what you were doing, you could turn that screw and now you're giving it a whole lot more fuel and you're making the engine run too rich. And what do you guys think that's going to do for the emissions? It's going to make the emissions, the smog, go way up, right? So with that, one of the modes, or one of the general trends, was to get rid of this main metering adjustment screw and go to a fixed jet. And what Briggs and a lot of the other manufacturers will say is that, hey, by going to a fixed jet, and let's see if I can get one that shows a fixed jet, it helps eliminate vapor lock issues and different things. But also, it's like you have a fixed air fuel ratio, and the only way to change it would be to change the jets. And that's not something that the normal do-it-yourselfer is going to do. People see a screw and they'll turn that. They're like, oh, what's that do? I don't know. I'm going to turn that screw. And I like to say that they see that screw, and by all means, they're going to screw it up, right? And then the engine's running really poorly. So they'll say it's related to vapor lock and it runs better. I think there's got to be a part of that to make the engine more tamper-proof, to make sure that the emissions don't get all out of whack by somebody just randomly turning screws on their carburetor. So we've gone to a fixed jet. But let me back up, because there was a couple slides I skipped over. In fact, we talked about this main metering, but there's another circuit of the carburetor that comes into play at low speed operation. and that's your idle circuit or low speed circuit. On a motorcycle carburetor, they like to call this like the pilot circuit. And this lines up with the carburetor that I have to show you guys very, very nicely. So the idea is this: at low speeds of the engine, low speeds of the engine means I have, instead of a lot of air moving through the carburetor, I have less air moving through the carburetor. So I have lower air speeds. And I may not get the amount of pressure drop I need through the venturi for it to make a low enough pressure to get fuel to draw through there. So that's not going to work. So what we have is an idle circuit or a low speed circuit that is below the throttle plate. The throttle plate, by the way, guys, is how by and large we control the speed of the engine. You want to control the speed of the engine, you just give it more air, right? The carburetor will then automatically mix the fuel with the air, but we control the speed of our engines. Like if you have an engine, like whether it's your car with a gas pedal or a chainsaw or a string trimmer or your motorcycle, right? You have a throttle, right? On your motorcycle, you twist the throttle. You're opening this throttle blade right here. When that throttle blade is closed, it's blocking the airflow. As I open up the throttle, what happens is I start to let more air into the engine, because now the throttle's more at an angle, and then now more air can go through here. At some point, I get enough air volume that I get the low pressure formed, and I switch over to my main metering system. Okay. But at lower speeds, at idle, when I'm not really working the throttle, I still need to give the engine a little bit of fuel. So what do? I have a low speed or idle circuit where I have a low pressure below the throttle plate. That low pressure will then draw fuel through the idle circuit, going all the way back down here to the float bowl. Notice that we have a idle mixture screw. It says adjustable jet. I would call this, I'm going to put down and use the text tool. I'm going to put down two names. An idle mixture screw or a pilot screw. Sometimes it's also called a pilot air screw. And that kind of depends on where the screw's at and how it works. So the idea with the one as it's drawn here in the image is that if I screwed this screw in, if I went clockwise with it, it would screw down and it would pinch off the fuel flow through the idle circuit, and that would lean out the mixture. Remember, lean is less fuel, rich is more fuel. And I remember thinking lean is less. So if I screwed it in, it's going to lean it out. If I move it counterclockwise, if I unscrew it, it's like opening up my garden hose, right? It's going to let more fuel flow through here, and that's going to richen up my mixture at idle. Now, remember that idle is, if I get my text tool up, low engine speeds. So this would enable me to adjust the air fuel mixture at lower engine speeds. Now, there are some carburetors where this screw maybe is just there to work on airflow, and it really depends on what screw, what carburetor you have and how stuff is plumbed up. So another way that these screws can work is they can be a pilot air screw. And so if I'm going to change my color, I'm going to draw a passage coming from this side of the carburetor, tapping in right here. Sometimes these screws are put in a position where they're not here, but they're over here. And what they do is they control a passageway for air to mix in with your idle circuit. So on those, if you unscrew the screw, it lets more air into the idle system and leans it out. If you close the screw, it brings in, it stops the airflow and it richens it up. Basically makes the screw the work the opposite way. So is it a idle mixture screw or a pilot air screw? The overall adjustment, or goal of what you're trying to do is adjust the low engine speed mixture is the same. They just kind of work in opposite directions. So now that we have some of those logistics out of the way, let's look at this on this carburetor that I have in my hands. So we will, again, we are going to pause our screen share, and then we're going to change our video over to the other camera. Boom. Now we're looking at our tabletop once again. I have an old AC Delco alternator table mat here. It's pretty cool. So here we're looking at our carburetor. Remember, the float bowl went on the bottom. We've taken off the float bowl, and I took out a couple of fixed jets. So here is my main metering jet. Here is my low speed or pilot jet on this engine. So for main metering, when I'm using the Venturi, fuel is flowing through that guy. For my idle circuit, fuel would be being picked up through that guy. And remember, both these are going to dip down into the fuel that's in the float bowl. Okay, so with that, we can kind of start to see these passageways here. I'm going to flip this over. And what you'll notice is that if I take the pilot, it kind of has a passageway. It goes out to the side, and that lines up with that screw right there. Main metering, passageway over to the side, that lines up with the screw more in the center of the carburetor. And if I look at this passage here, I'm going to draw right on this thing to make it really evident. That also has a line there that goes to the front side of the carburetor where air, if I put some red on this thing, where air goes in there as well. So air can mix in to the low speed or idle circuit from the front side of the carburetor. And what controls how much mixes together is this screw right here. So this screw can work one of two ways, depending upon if it's affecting the air more or the fuel more. But traditionally, if I tighten the screw, it's going to richen up the mixture. I'm sorry, if I tighten the screw, it's going to lean up the mixture because it's pinching off the fuel flow. And if I loosen it, it's going to richen up that mixture. And that screw would help adjust your air fuel mixture at lower engine speeds. You're probably thinking, well, wait a minute. Okay, that's that screw. Well, what's this screw right next to it? What's this guy doing? Well, this is your idle speed screw. So this screw would actually move the carburetor slide on this engine and basically can make the engine run faster or slower, but it would not affect the air fuel mixture. Okay, so that's your idle speed screw. This is your idle mixture screw. Sometimes that would be called a pilot air screw, depending on the carburetor. And you can see how it goes through the different passages, and you kind of get a feel for how small these passages are in this carburetor. So now we've looked at this thing a little bit. I'll flip it over. My jets are falling out. Whole thing really needs to be cleaned. But now you've seen both screws. Now I'm going to go ahead and take both these screws out, if I can, here with my 90-degree bent screwdriver. And you might notice that there's little springs underneath these screws. The springs keep tension on the screw, and that's to keep your adjustment. Without a little spring there, it wouldn't, if you adjusted that screw, it wouldn't keep its adjustment. It would just move around due to engine vibration. So again, this is your idle speed screw. It's just moving a little stopper, which would move the carburetor slide. This one is the idle mixture screw, and it's going to come to a point when I take it out, and it's really gummed up in there. I mean, this thing is probably going to be pretty nasty when we finally do get it out of here. Almost there. Okay, boom. There's a spring underneath there. You can see it comes to a point. I know the camera doesn't focus on that really well, but it comes to a point. Here's my spring in there to keep that adjustment. And if I had an engine that was running poorly, maybe that was hesitating, I would definitely take this out and I would shoot carburetor cleaner through there or brake cleaner and try to clean out all these little tiny passages in here. I'm going to put this carburetor in the ultrasonic cleaner. So I'm going to take all this stuff apart before I dump it into my vat of cleaner there, if you will. And I have a video of cleaning a few different carburetors using the ultrasonic already posted to YouTube. So if you guys haven't checked those out, you should do that. But now you've seen the idle circuit and its passageways, the idle speed screw. There's a few other things on this carburetor that we haven't talked about, and we're going to jump into those before we wrap up for today. All right, so let's get the screen share going again. And with that, let's see, there it is. And we will change our video camera. Boom. Okay, so now we've looked at these things on a real carburetor. And when you guys service your carburetors, I really want you to try to find these parts if you can. And remember that the idle speed is going to be the idle circuits for low speed, and the main metering is for high speed. So you can then, once you understand how it works, you can say, well, when is my engine having a problem? What circuit do I need to pay more attention to? All right, moving right along. This slide here is just showing you, hey, as I open up the throttle, that lets more air into the engine around that throttle, and that's going to cause the fuel to more fuel to be delivered from the main metering system. All right, we'll clear those out and we'll keep going. Got the idle circuit out of the way. All right. There are several small engines with primer bulbs, and this does relate to some of your test questions that may drive you nuts. Some of these primer bulbs are, as it says in this slide, full of fuel at all times, and some of them just have air inside. And it really depends on how it's set up in that carburetor. The idea with the primer bulb is if you have an engine that, you know, maybe it would take quite a few pulls of the rope to get it started. If I can get a little bit of fuel drawn up from the fuel tank into the carburetor, so it's well on its way to going into the engine, when I first pull the rope, it's going to allow me to start that engine a little bit easier. So the primer bulb is going to do just that. It's either going to basically act as a device to create a vacuum and draw fuel up into itself and then press that fuel through the main metering circuits of the carburetor or through a discharge port in the venturi. Or it might just move air where you're basically moving air to push fuel through something. So some of these bulbs will be wet bulbs. They're filled with fuel. and some of them are dry bulbs. The dry bulbs usually last a little longer. The wet bulbs, because they're exposed to gas, over time, that gasoline is going to deteriorate that rubber. And this is where we tapped into the alcohol that's in our fuel. Of course, it deteriorates those rubber components that little bit faster. And so changing primer bulbs is something that we, commonly have to do on a small engine that gets 4, 5, 6 years old. Now it's hard to start because the primer bulb is starting to crack. Okay. I actually pointed out some of the air bleeds before, but remember the air bleeds are there to help mix air with the fuel to end up with the right air fuel mixture when it's done. There's a weird concept, and that is that fuel will only burn when it's been mixed with air and it is fully vaporized. So I got to get the liquid fuel to turn into a vaporous fuel in order to burn it. And so how do I do that? Well, by applying heat from the engine, but also mixing it with plenty of air and ripping up that fuel into tiny little droplets. And that's what the carburetor tries to do with these various air bleeds that are in it. So there we can see how there's air bleeds. There's also transitional holes to help you have a smooth transition from the idle circuit, which the idle circuit discharge ports there. Here's my transition circuit or off idle circuit up to main metering, which is going to discharge here. So we want to have a smooth transition between low speed and high speed operation. So a lot of carburetors that have a idle circuit on them will have transition holes or off idle ports to help you make that smooth transition. And all these little passages need to be clean inside this carburetor. All right, moving right along. So you saw some fixed jets on our carburetor here that we were holding up, and keep in mind that these jets would need to be cleaned out. And then if I wanted to change the air fuel ratio, I would physically have to change out the jet. So this jet here unscrews, and I can screw another jet inside there and make the jet have a bigger hole that's going to richen up the mixture. If the jet is a smaller orifice, a smaller size hole in there, that's going to lean out the mixture. So in the racing community, we would change jets pretty frequently on our carburetors to try to get the best air fuel ratio depending upon what ambient conditions we have. So I might even run a bigger jet in the morning when it's nice and cold out than I would in the afternoon when it's hot out, because the air density changed, and I would change the jet to compensate for that, to try to keep my air fuel ratio where I wanted it. And it might seem silly, but I remember early on with my son doing some racing, and we were just in little go-karts called kid karts. We changed his jet between the morning and the afternoon, and he picked up a half a second a lap, which in the racing world, half a second a lap's huge. That's a huge gain by getting the right jet size in there, which gave us the right air fuel mixture and allowed the engine to make the most amount of power. So yeah, got good at changing a lot of jets over the years. All right, so moving right along. Here's a couple better shots of those transition holes and the off idle circuit. They're showing like a screw in style pilot jet. We've looked at that on a real carburetor. And there's several different styles of carburetors. Here we have a side draft carburetor. And I haven't talked about this yet, but see, if I look at this, I can have basically, or actually this one's a weird one. Here's the choke. So this is an updraft carburetor. Air goes in here, flows up to the engine that way. And so it's a weird style of carburetor. Whereas like This one I have in my hands is a side draft because air flows in through it sideways. We have a lot of carburetors on our automotive engines that are downdraft carburetors where the air flows in from the top and goes through to the bottom. Now, this thing's talking about this vent, internal vent, external vent. What are we talking about? Well, the float bowl has to be vented. As you start bringing fuel into the engine, if you don't have the float bowl vented, what will happen essentially is the engine will run out of gas because you can't get the fuel back in the carburetor fast enough. And you'll end up where if you don't let some air in there to compensate for it, you'll end up with essentially it's like if you were drinking from a bottle and you didn't let any air in, you couldn't get any, whatever your favorite drink is, right? Soda or whatever, you couldn't get any liquid out of that bottle because you got to let air come in there and take up the place of that liquid. So we have to have a float bowl vent. So this one we can see it's internal. This one we can see it's external, but every float bowl has to be vented. Which if I clear out these drawings and I keep my slides going, I'm going to, oh, here's some different carburetor designs. We were talking about that. I guess I should point that out. So there's an updraft design, downdraft automotive style. Here's a 2-barrel carburetor. And then there's our typical small engine side draft carburetor. So that's the direction of the air travel through the carburetor. Briggs & Stratton does have some weird carburetors. And you're likely to see these on small engines. The idea was that, hey, it's a simple engine. It's not having to haul the family and kids around and tow a boat or something. It doesn't need to be that complicated. It just needs to maybe mow my grass or something. So they, for a long time, would try to make the carburetor as simple as they possibly could. And so they did that with designs like the vacuum jet here, where it didn't have a float bowl. It used the gas tank as a float bowl. Essentially, it didn't have an idle circuit either. It had a main metering circuit. And so that enabled the carburetor to be as simple as it possibly could. So you might have one of those on your engine. So there's another shot of that vacuum jet. And here's how the vacuum jet would plug together is it sits right on top of the gas tank. So if you have a carburetor that seems like it's part of the gas tank, it's bolted to the top, it's likely either a vacuum jet or a pulsa jet. So the vacuum jet was more old school, so an older design. And the problem with the vacuum jet is that as the fuel level in the gas tank changed, the air fuel ratio that the engine was running would change. Because essentially it was like changing the fuel level in the float bowl. As the engine ran low on gas, it would lean out. If you fully filled the tank, it would richen it up. So they decided, hey, that's changing too much of the air fuel ratio. It's creating an emissions problem. We want to keep the carburetor really simple. So they modified that to the vacuum jet, which basically then had a little fuel pump deal in there, and it would pump the fuel from the gas tank to a little secondary well in the top of the gas tank that almost formed kind of like a little float bowl. So it was always full of fuel and it worked that way. But either one of those carburetor designs did not have a traditional float bowl with a traditional float assembly in there. And there's another shot of that pulsa jet. So if you took it off the top of the gas tank, you'll notice it's got 2 tubes, a couple weird passages and stuff that the vacuum jet didn't have. We got some slides here with the importance of changing fuel filters and that type of thing. But what I need to do is I need to back this up because we really need to talk about our float bowl. And one of these slides, it's not showing me, but I really need a slide that shows me about the float mechanism. So let's start with this slide right here. It's talking about the bowl vent. And we were talking about that before, and we saw some other pictures. So this carburetor has kind of an internal bowl vent. So here's my float bowl. Here's my bowl vent, which essentially goes to outside air above the throttle. Here's my throttle plate. I'll draw them a different color. Here's my throttle plate right here. And the idea is as the fuel goes down, I need to let some air from the outside in to take up that spot until I can use my fuel delivery to fill that float bowl back up. Now, you know what you're not seeing in this slide is the actual float pontoon. I'm going to draw him. I'll draw him, I guess, purple here. So it's a different color. I don't know how well that purple is showing up, but a real float system has a little boat in there, if you will, a little pontoon, little float assembly that floats on top of the gasoline. And then what that float does is it pushes I'll draw it over here. It pushes a needle into a seat, which controls how much fuel. If I draw, let's say, a red gas line here, it controls how much fuel can enter the carburetor. So the one thing about the float system or circuit is it's important, arguably the most important circuit, because it affects all the other circuits of the carburetor. And I think to really show it, because none of my pictures in this presentation really do a good job showing the float, so we're going to show that to you on the real carburetor. So let's switch over one more time, guys, as we wrap things up. Let's switch you over, change the video to the other camera. There we go. And we're going to stop that share. All right. So here is that carburetor. This is my float pontoon there, and he would sit right inside the top of the float bowl like this. Now he's going to pivot off of this little hinge. This little float pin there provides him a pivot point. And if I can piece this thing back together, you can see that when it's low on fuel, the float's going to go down. And when the float bowl fills with fuel, this thing's going to float on top of the fuel, so it's going to push it up. When it pushes up, this little part right here of the float pushes on this needle valve. And if I can get that little needle valve on the end of my screwdriver, you can see it comes to a nice little point. It's got a little rubber tip on there. It pushes on that needle. That needle then goes into a seat, and that pinches off the fuel flow. Because if I look at the side of this carburetor, I can see that there's a fitting right here. This fitting is where the fuel goes in to the carburetor. So it goes into the carburetor there. How does it actually get into the float bowl? It has to pass between this needle and seat. So that's how we regulate how much fuel enters the float bowl. If I have more fuel in the float bowl, it's going to make the whole engine run richer. If I have less fuel in the float bowl, it's going to lean out the air fuel mixture. So the position of this float and its adjustment, which basically is adjusted by bending this little tang on the float, is important because it will affect the air fuel ratio of all the other carburetor circuits. So with that, if I switch this back to our screen share, today, as we've looked at carburetors, really, we've only talked about a few of the circuits. We have talked about now the float. I'm just going to put CKT for circuit, kind of shorthand there. We've talked about the main metering. And we've also talked about the idle circuit. We've only talked about 3 circuits of the carburetor, but you know what I'm going to do? I'm going to sneak in a 4th one that's super easy to get, and it's really easy to show. Now, what's the choke circuit? The choke circuit is essentially choking off the airflow for the engine. So I'm going to make the image big one more time here. This is my choke valve. And so what happens when I put the choke on, what I've done is I've closed that valve and I pinched off the airflow. If I turn the choke off, I open up the airflow. So the choke, think I'm choking off the airflow. Well, if I choke off the airflow, it essentially increases the fuel flow. It richens up the mixture a whole bunch. Remember when I said the fuel only burns as a vapor? When the engine is cold, it does not do a good job of turning liquid fuel into a vapor. So how do we compensate for that? We turn the choke on with the idea that if I give the engine a whole bunch of fuel, some of it's going to turn into a vapor and it's going to get the engine running. Once the engine starts running and it starts warming up, it does a better job of turning the fuel from a liquid state to a vaporous state so it can burn. So as the engine warms up, I can then take the choke off and then have the engine run. And you'll notice if you let the engine run too long with the choke on, when you finally do take the choke off, now the engine runs a lot better. Because you're getting better, you're not running so rich. You're getting better to a more ideal air fuel ratio. So hopefully some of that stuff made sense to you. I have other videos and presentations on carburetors. Briggs and Stratton on the Power Portal has some great video clips related to carburetors as well. And really, it's one of those things where I think it helps you if you take the carburetor apart and you look at the parts and pieces as you're going through it. Now, because carburetors vary, right? You've even seen 1 barrel, 2 barrels, updraft, side draft. You guys are likely, you've seen vacuum jets and pulsa jets today. You might have a carburetor where you look at it and you're like, hey, where's that? Or what's this? Don't be afraid to take a picture and, circle a spot and ask me, well, what is that? What am I looking at? We should be able to piece those together. Okay. All right. So I see Eric's got a carburetor in his hand. So Eric, that is likely off of a 2-cycle engine, correct?
Yeah.
And that is what I call a diaphragm style carburetor. And so we're going to talk about that dude next week. That's going to be our hot topic, that diaphragm style carburetor. And so what's unique about that carburetor is it does not have a traditional float in it. And the reason it doesn't have a traditional float in it is because an engine, a 2-cycle engine that you'd find that carburetor on, will be operated at all kinds of angles. Think about your string trimmer, or what people will commonly call a weed eater, right? Sometimes you throw it on its side and you use it to edge your lawn. Sometimes you're, using it horizontal. You're using it all kinds of angles. You'd also find that carburetor in a chainsaw. And again, a chainsaw, you're going to have all kinds of crazy angles, right? So a regular carburetor with a traditional float that has a little, boat, if you will, floating on the gasoline, that's not going to work at really radical angles. So that carburetor is designed to get away from having a traditional float, and it has essentially like a metering diaphragm. It also has a built-in fuel pump because, again, you can't allow gravity to bring the fuel to the carburetor if you're operating it upside down. So that carburetor is 2-in-1. It's still your carburetor, but it's also a built-in fuel pump. So on one side of it, hold it back up to the screen. So flip it 90 degrees. Okay. So right there, what you have is your fuel pump diaphragm. Underneath that, if you took that screw out of there, that'd be your pump diaphragm. And if you flip the carburetor 180 degrees so I can see the other side, that is your metering diaphragm underneath there. So it's got 2 diaphragms. One takes the place of the float. The other diaphragm takes the place of a fuel pump. So it's a fuel pump and a carburetor all built into one. There's a lot of stuff going on in there. And it has 2 thin little diaphragms in there that make it work. That's the style of carburetor that is really messed up by the alcohol in the fuel. And when those get to be about 5 years old, Usually by that point, the alcohol will have eaten up the diaphragms enough where they don't flex like they're supposed to flex, and the engine quits running how it's supposed to run. So it's not uncommon, like I said, when it gets 4 or 5 years old, they either have to rebuild that carburetor, put in new diaphragms, or replace it. A lot of times you can get those carburetors online for less than $50.
Yeah.
So, or you can replace the diaphragms yourself and maybe spend, I don't know, 10 or 15 bucks. It kind of depends on which way you want to go. There are some failures that you can't fix in one of those with just changing out the diaphragms.
So can I disassemble this one for the project?
Yeah, you can. You
Okay.
can. Just keep in mind that it's, you know, it's a different style, right? And
Yeah.
it's that carburetor that, like, my automotive teachers, they'll understand the carburetor I kind of went over today, because that's more like a car. Those carburetors is what drives everybody nuts. And it's like they're complicated through their simplicity. That carburetor, they recommend to not use regular carburetor cleaner on it. They want you to use brake cleaner on it, because if you want to reuse those diaphragms, the regular carburetor cleaner will eat up the rubbers. So they say clean them out with brake cleaner.
Oh, really?
Or get a little ultrasonic cleaner to buzz that carburetor and get all the junk out of there.
Cool.
There are times with that style of carburetor, because the passages are so small on the inside, where I just couldn't get it cleaned out, or I had an accelerator pump that had failed and you just can't service that. So there's sometimes where, a lot of times I'll just rebuild them. Sometimes that doesn't fix the problem and I just have to replace them. But yeah, that's a good one to do your project on. It's a little different. We'll talk about it next week. I do have some videos about that style already made. And if you go through the still training, they should do a better job explaining that style of carburetor. Where Briggs and Stratton, the power portal, won't really go into that style of carburetor because it's not used on Briggs and Stratton engines much. The still training will go into that style. Okay, so it's a unique deal. But you know, every fuel system, I don't care if it's fuel injected or carbureted, if it's a diaphragm style carburetor like you have, or this more traditional side draft that I have in my hand, it still has to meter the right amount of fuel with the amount of air that's going in the engine. And it's got to allow you to control the speed of the engine and, you know, get that fuel there with all the different speeds and loads of the engine. So cold startup, all that type of stuff, it always still has to meter the right amount of fuel with the amount of air that's going in there. So those things kind of stay the same no matter what you're working on when you think about air fuel mixtures and stuff. All right, good deal. Well, thanks for showing that to me, and thanks for hanging out with me, guys. Tim, it's good to see you. We also got Jeff on the line, so I really appreciate it. I haven't added in the points yet, but fear not, every class session we have, Canvas allows me to do an attendance chart, and so I'll give you guys bonus points for being here with us today. And I certainly appreciate you being there, so I'm not just talking to myself on here. And yeah, your questions and stuff are always welcome. Carburetors, I mean, it's carburetors. The bulk of the problems you guys will find with your engines are usually related to the carburetor getting all clogged up full of stuff, just like the one I had in my office here. That's a real common theme. So don't overlook that. Yeah, you have compression issues and other things. Yeah, right on, Tim. I see Tim's got a carburetor. So that one, hold it closer to your computer or camera, would you? All right. So that is a great example of what looks to be a Pulsa-Jet style carburetor, because I see two tubes going to the bottom. So that's a weird one. It doesn't have a traditional float. It's a Pulsa-Jet, so it's got like a little fuel pump diaphragm thing in the bottom, and it has a little storage tank for fuel inside there. It might be a vacuum jet. It's kind of hard to see. It does have a primer bulb on the side. So again, same thing holds true. Passages will get clogged up and the engine won't run right, and you'll drive yourself crazy trying to pull start it a million times to get it started and running. A lot of those little rubber parts, and there's your diaphragm style. Yeah. A lot of those little rubber parts will just fail and they fail more frequently now because the alcohol that we have in the fuel. It's just how it is.
Is it possible I can clean this one up and make it work?
Yeah, it's possible with both of those to clean them up and make them work. Every once in a while, you will get one that no matter how clean you make it, new diaphragms, you do everything, and it could have just failures on the inside. So I have had some that I can't bring back. The other thing we didn't talk about is that the throttle shafts can actually wear, and that causes a vacuum leak. So there are some cases where it's either too plugged up or just too worn out, and you can't bring it back. But I would say a good, 9 times out of 10, you can usually clean them and service them and put in new diaphragms and bring them back.
The lines were completely disintegrated inside the tank.
Yep.
And now I have two different sizes. I have one that's might be a little bit loose going into the tank. Will it still work?
So it's loose where it fits to the tank.
Yeah, where it up.
Yeah.
Oh,
so it'll work, but what will happen is if you use your chainsaw at an angle, it's going to start leaking fuel all over the place. So I don't think I'd recommend that unless you figured out a way to seal it up. Because with the chainsaw, you're going to have it at all kind of crazy angles, right?
Yeah.
If you're out there trimming trees or whatever. And so you really want that gas tank in that saw to be sealed so that it doesn't leak fuel all over. Also, chainsaws get pretty hot. So it would be pretty easy for it to start leaking fuel, and then all of a sudden your saw is catching on fire or something. So I would try to get a fuel line that's either tight to the opening in the tank, or see if there's like some type of grommet or rubber valve that seals it up, because you really don't want to have fuel leaks there. But you could use that line certainly to at least get the saw running, to verify like, hey, does this thing work? Is the carburetor working? And then from there, once you get it running, then you could actually fix that part and make sure that the lines are tight on there. You wouldn't want any lines to be loose, like the fuel feed line that draws the fuel from the tank to your carburetor. You don't want those lines to be loose on the carburetor, because it'll just suck air and not fuel, and your engine will never fire up and run, right? So another common thing with you had showed me 2 carburetors. They both had little primer bulbs on them. The primer bulb is there to help prime the carburetor and get it running. If you have one that like you push the primer bulb, you can run the engine for a few seconds and then the engine dies out. That's usually a sign like the main metering system is clogged up or something, and you can get gas to the carburetor by using the primer bulb. But then once it runs out of fuel that was brought up to it from the primer, it shuts off. That tells you that your main metering is either clogged up or not working, or the fuel pump diaphragm is not pumping the fuel from the tank to your carburetor. And so the only way you can run it is by manually doing the primer valve. So those are both good ones to do.
Thank you, Professor French.
Hey, thank you guys. Thank you for being with me. I'm going to let you guys get on with the rest of your day. Great job. Great work out there. Okay. Take care, everybody. You guys take care. We'll see you next week.